time we stopped, thank you. So last time we stopped, here we did an example of the AC to AC voltage controller, or the phase controller, phase voltage controller. And we did the example in the case where alpha was 30 degrees, and we saw this output voltage waveform here on phase A. I can go through another example quickly of, so there's several different operating conditions for this circuit. So in this case, we always had, we either had two devices on, or we had three devices on. When we had three devices on, we had a balanced circuit, and the output voltage was equal to the phase voltage. So during these periods, we had a balanced circuit. During this period here, I had a balanced circuit. During this period here, I had three devices on. As soon as I have three devices on, that means I have a balanced source and a balanced circuit, right? And the output voltage on the load will be equal to the source voltage of that specific phase. And then that's the case when the three devices are on. So we had cases at some times where three devices were on. We had cases where two devices were on. In these cases, we had the voltage was equal to some of the line voltage. So this is in this portion here we had two devices on. In this portion here we had in this portion here we had two devices on. In this portion here we had two devices on. This portion here we had two devices on. So as long as there are two devices on, we are not on, the output voltage does not equal the phase voltage. Right? When three devices were on, the output voltage equals the phase voltage. If you increase alpha, you end up with a condition. So we drew this voltage waveform, and of course for phase B and C, they're exactly the same but phase shifted. Phase B and C will be exactly the same as phase A, but phase shifted with respect to phase A. And the corresponding device currents, of course, how would you draw current in switch 1? I would have to go to, I don't know if I have the, here. If you see what we had here I said that I have 6 and 1 on, and then 6, 1 and 2, and then here I had 5, 6 and 1 on, which means that during this interval here, during this interval, there was current in switch 1, right? So at some point you would have to draw the current in switch 1. And the current in switch 1 is what? Is if you go to switch 1 is the positive current from phase A, right? So you would, and we know this is a resistive load, which means that the current will have the same shape as the voltage on the resistor. So basically, since we know the output voltage on the resistor looks like this, then I can draw the current to the resistor. I know it's going to look also the same shape, right? So it will look like this, exactly the same shape as the resistor voltage, right? So this is the output voltage. It will look exactly the same as the current, because here, and then this is what I have here. The current here looks exactly the same as this. This is the voltage on phase A, and this is the current through switch 1. Current through switch 1 was the conducting current from the source to the load. So since it's in series with the load, then it has to be the same shape. Right? These are both the same shape. Right? So you can do the same thing with the rest of the switches. I mean, the rest of the switches, this is switch 2. Switch 2 is in which phase? We go and check, and it will be in phase C return. So we go to C. Phase C is this voltage here, and again it's the same current. That it's the voltage shape here. We flip it, since I'm drawing all the currents with a certain polarity. I'm drawing all the currents as positive. Since again the reason we draw that is because of the notation we assumed. We always assume that if we have a thyristor, that current will be flowing. This is this is the current flowing from node A to K. So we're always drawing thyristor current in a certain direction, right? So, and it will always conduct in a certain direction. That's why we draw it as always as positive. right? Because it's with the notation that we've assumed. We assumed notation was like this, and it's always going to flow like this. That's why they're all drawn as positive. And they all have the same shape as the corresponding voltage waveform. Okay? So that's okay. Now, if you make alpha greater than 60 degrees and all the way up to 90 degrees, then you have a case where only two of the devices are on. I'll go through that very quickly with an example. We'll draw that as well. And no, not this. Okay, I'll draw this table that I had last time, which was phase A, phase B, and phase C. Remember when we did the top devices were 1, 3, 5, and then the bottom ones were 4, 6, and 2. So 1 is conducting current from the source to the load, source to load, source to the load on the various phases, and this is the return from load to the source. Okay, and how did we go about doing this? We said that initially we started looking at these points. These were the critical. Remember, we had some critical points in where this was positive and this was positive and these were negative, and something was happening at this node here, and this was another node. This was another node. This was another node. This was another node, and this is how we chopped it up into 6 periods of 60 degrees each. Right, and we said that if they were all diodes, we start with the all diodes case, right? If they were all diodes, which diodes would have conducted? This is phase A, phase B, and phase C. If they were all diodes here, and they were all conducting. If they were all diodes, then they would all be, then I had 3 devices always connected, right? It's like having a wire if they're all diodes. Then I would have phase A positive, phase C positive, and phase B negative or lower one, right? Phase C, phase B bottom one, which is 6, right? And phase A and C top ones, which is 1 and 5, right? So we said that here in this interval I would have devices 5, 6, and 1 on, and then we said that I would have the next one I would have 6, 1, and 2 on, and then we'd always drop 1, right? So 1, 2, and 3, and then 2, 3, and 4, and 3, 4, and 5, and 4, 5, and 6. This was the all diodes case, right? This is our reference always, right? This is always our reference. Now, if I want to have 30 degrees, we did. How about if I have alpha equal to 90 degrees? If I have alpha 90 degrees, where am I going to fire thyristor 1? Where A is. Exactly, right? Where I wrote the letter A. So why is that? Because thyristor 1 was going to be fired, or if it was a diode, it would have started conducting here. So if I measure alpha, 90 degrees from where the diode would have conducted, right? So I would start conducting, I would fire thyristor 1 here. Right? Thyristor 2 would be fired 60 degrees later. Thyristor 3, I chose 90 because it's easy because I have these intersection points, right? So it's easier to draw. 3. 4. 5 and thyristor 6 would start conducting. This is where I'm firing thyristor 6, right? So let's start with, where we fire thyristor 1, because we have to start somewhere, and then we're gonna wrap around the drawing. But let's start here. If I fire thyristor 1 here, that 1 is where? 1 is the top on phase A, top device on phase A, right? So let's see what's happening here. Phase A is the highest voltage, right? So if it's the highest voltage, definitely if I provide a firing signal for thyristor on phase A, then the thyristor will conduct. Right? It's the highest voltage, right? So 1 will start conducting here. So what devices would I want to know what devices I will have conducting during this interval, for example. We said 1 will start conducting because definitely it's the highest voltage here. How about the other two? How about the other two? What was happening before? Before I had 6 conducting. 6 was started conducting here. So 6 is what? 6 is the return of phase B. Phase B is here. So does it make sense that current can go from higher voltage to a lower voltage? Right? If I have thyristor 1 on, right, I can have the current can go back through phase B, because phase B is a lower voltage and device 6 was on, right? Current has to come from the source and come back through somewhere else, another path, right? So in this case, it's A is the highest, and I provided a gate signal for thyristor 1. So thyristor 1 was the highest voltage, right? Current will flow from a higher voltage to a lower voltage, right? Even if the two voltages are positive, or even if the two voltages are negative, right? It will go from the higher voltage to the lower voltage, right? So now I have a higher voltage at phase A, and then I provided a firing signal for thyristor 6 here, right? For thyristor 5 here. 5 is what? 5 is the top device on phase C. Top device can only conduct current. It will take current from the source to the load. If it's a higher voltage than the phases, the voltages in the other phases, right? I can only take current from phase C to phase A if phase C is higher than phase A, right? I cannot, in that case, phase 5 will be on and 4 would need to be on, right? But now 1 is on. I provided a gate signal for thyristor 1 on, and the voltage on thyristor on phase A is the highest. So this will easily conduct, right? And then the current would like to go back to the source, right? It has either phase B to go back or phase C to go back, right? So phase B to go back is device 6. Phase C to go back is device 2. Is 2 on? 2 is not on until here, right? 2 is not on until here. So 2 is not on. So 2 is not an option to go back. Current will not be able to go back through phase C because device 2 is not on. So the only other option is 6. 6 was on already. It was on. Is there a reason for it to turn off? We see 6 was on. It's phase B, the negative. Phase B negative was on here. Is there a reason for it to turn off? The only reason for it to turn off is if you're trying to push current through it in the opposite direction, or if you're trying to push current through device 3. You're not trying to do that. 3 is not on. 3 cannot be on anyways. That's not available for you to conduct current through it at all. Right? So current will go from my source on phase A back through phase B on device 6 because device 6 was turned on here. So current will go from phase A to phase B. So which devices do I have conducting in this period? 1 and 6, right? Or 6 and 1. Let me write 6 and 1 because we will, for a reason. How about here? This is in this part here. How about here? Also, 1 is on. It's still higher than B. voltage on phase A is still higher than voltage on phase B, right? So, and C is the lowest voltage, but for C to return, for anything to return from phase C, C is the easiest for current to return from, because it's the lowest voltage. So phase A and phase B would like to push current through and return them, go from the supply and return through phase C. But phase C cannot do that unless I fire thyristor 2. Thyristor 2 is not fired until here. So until this point, phase A voltage is higher than phase B voltage, which means that always I can push current from phase A and return the current from phase B if devices 1 and device 6 are on. So this is the case all the way until here. So here, all of this period, it's 6 and 1. Right? At this point, what happens? Phase B becomes higher than phase A. Phase B higher, so what happens? I want to actually push current from phase B positive, 3, right? Phase B positive, and return it through 4. I don't have 3 on yet. I don't have 3 on. And I don't have 4 on. Right? Right? What do I have to turn down? I can turn here on. Here I provide the gate signal for 2. 2 is phase C, lower one, right? 2 is phase C, lower one. So current can go back from phase C, right? I would like, and which device was on here as well? 6 and 1 were on. 6 and 1 were on here. Which device am I asking to change the polarity of current through? So 6 is the lower on phase B, is the return, right? Here I provided a gate signal for thyristor 2 here, right? Is it easier to return from 6 or 2? 2 is phase C. It's the lowest, the most negative, right? So current would easily find the route to return through phase C, negative, and I just turned on phase 2 here. Here, what's going on? Here I had 1 bringing current from my source, going back through device 6, right? I am no longer able to do that because actually phase B and A swap polarities. The voltage difference between them swap. It's like I want to push current back through phase A, right? It's like I want to push current back through phase A, and I want to bring current from phase B. So it's like I want to have devices 3 and 4 conduct. And I don't have that luxury. They don't get their gate signals until 3 and 4 get their gate signals here, right? So if 2 gets its gate signal at this point here, right? It is the lowest voltage. If there's another device that is already conducting, that is able to bring current from my source and back through device C, that is the device that will be conducting. So what is that device? No, 6 cannot bring my current from my source. 6 is bringing current from my load back to the source. Here I have 6 and 1. 6 is the return. So it's useless because C now is the easiest return. So 1 will stay on, right? 1 will stay on. 1 stays on, meaning I can take current from my source through phase A, bring current back to the source through phase C, right? So here, these 2 will be the ones conducting, right? No, A, sorry. A is the red. So these 2, current will come from my source on phase A back through phase C, right? So I will have 6. So here I will have which devices on? 1 and 2, right? 2 is for phase C, low, and 1 is for phase A, high, right? So here's 6 and 1. Here's 1 and 2. Which devices are here? 6 and 1, 1 and 2, 2 and 3, 3 and 4, 4 and 5, 4 and 5, and then here 5 and 6. If you go through it, this will be the logic. So now, if I want to draw phase A voltage, right, then I will have to look at any time device 1 or 4 are conducting, and then I will see what's the corresponding device, which other phase is conducting with it. So here I have 6 and 1 conducting, so this is a period of interest. So here, let's look at here. Here I have 4, so this is interesting, right? Because 4 is conducting, so it's connected to phase A, right? How about here, 5 and 6? 5 and 6, nothing on phase A. Voltage is coming from phase C back to phase B. What's the voltage on phase A? It's an open circuit, it's 0, right? So here there's nothing. How about here? Here it's 6 and 1, so 1 is there. And then here also there's 1 and 2, so all of this period I expect to see some voltage on phase A, right? How about here? Nothing. Here, yes, I expect to see a voltage, so I have 4. And here I expect to see a voltage because I have 4 as well. Right? Anytime I have phase A involved, I expect to see current through it. If A is not involved, I don't expect to see current flowing through it. Correct?
So, can you show us what the current will be?
2 and 3? 2 and 3. So current will come from phase B back through phase C.
So just down.
Yeah. From phase B back to phase C. Nothing is going to flow through phase A. So remember, we had my load looked like this. This is phase A, B, and C. If current goes from phase B back through phase C, right? Nothing is happening on phase A. There's no current, there's no voltage, right? So that's why I chose the devices. Anytime I see a device that has phase A involved, that's an interesting point for me. These are interesting areas for me, right? So now we see what is the corresponding voltage during the periods where any device connected to phase A is conducting. So if 6 and 1 are conducting, I have A is, 1 is phase A, top. There's one is A, and then 6 is B. So VAB over 2 will be my voltage. So VAB is my red voltage, right? VAB over 2 is the red voltage that I have here. So it's the red where? Here at this point, it's the red. Here it's, this period it's what? 0. Here it's 0. Here it will be the red all the way until this point, right? And then here I have 1 and 2, right? 1 and 2 are A and C, VAC over 2. Here this is VCA, I will draw VAC. VAC would look something like this. Right, so voltage will look like this all the way until here, correct? And then 0, nothing here. And then it will be a mirror of this. So what do I have? 3 and 4. 3 and 4, AB. So it's AB but with a negative sign. So it's 3 and 4 is like BA, right? Which is AB with a negative sign. So it's actually AB but with a negative. So it's the AB waveform but in its negative half cycle. And then 4 and 5 is CA, which is like AC in the negative half cycle. This is my AC waveform in the negative half cycle. It's like this. This should continue. This is the green, okay? Okay? So this is my waveform. Yes, sir.
So, stop getting it. Why do we want to obtain this waveform for three-phase?
Why? Because we said that sometimes you don't want to put the full voltage across your three-phase load. Like in motor starting, we said motor starting. I'll talk about applications next after we finish the waveforms. Motor starting, light dimming, heater control, all of that. All of these applications are AC applications that the way you would control the power through that heater, or the way you would limit the inrush current in the induction motor, or they limit the inrush current of the transformer, or whatever, is by starting with a small voltage and then increasing it. How do you do that? The only way to do that is, the simplest way to do that is with a AC to AC voltage controller. So I can, because now do you agree that now, versus the case where they're all diodes, what was the voltage on phase A? In the case where they're all diodes, the voltage on phase A was like this. Right? And let's take only the half cycle. With the half cycle, this was the blue, I had the blue voltage. Versus now I have this other waveform, which has a higher RMS value. The blue has more area under the curve, means more RMS value. Right? So basically I'm able to control my RMS value of the voltage. That's what you do. Like in AC to DC conversion, what we were doing with alpha, with the firing angle was, okay, I want to reduce my voltage. I want to be able to bring down my voltage from a certain value all the way until the diode case. Here, I want to be able to bring down the voltage from my all diode case down to 0. Why? Because I would like to control the voltage that I'm applying across my load. Right? With the induction motor, you're controlling V and F, right? With a motor drive. With a soft starter or a motor starter, we're controlling only voltage. And this is a way to control it. With light dimming, we're controlling only voltage. The most important applications are either motor starting or what we call static VAR compensation. I will talk about that. I touched upon it briefly when we were very beginning of the chapter, but I will talk about it as an application next. But from a waveform drawing, you're okay with the waveform drawing? But this is a different condition, right? Here I only have 2 devices on, never have 3 devices on at the same time, unlike the last case here. So, oops. So this is, I didn't draw 75 only because I didn't have the nice grid lines, right? I drew 90. 90 would be what? 90 would be, I brought this, instead of 75, you start a little bit later, and you go all the way down to the 0 point here, right? What's going to happen beyond an alpha of 90? Beyond an alpha of 90, you will start a little bit even later, and then you will go all the way to 0, and you will have a place where the voltage output is 0. So that's what they have. That's what they've shown here. So draw this. I will not draw this one. It's very similar to what I just did. It's also 2 devices or none. Like the case I just did with 2 devices or none, it's a very similar case. So, as practice, do a case where alpha is 120 degrees. And it may help if you draw more grid lines. It may make it easier for you to do the drawing. So that's this case. This is the case of a star-connected source and a star-connected load with this AC voltage controller between them. How about if the load is delta connected? Okay, before we go there, so as we said, we're controlling the value of voltage. So as I change alpha, as I increase alpha, I can bring down the voltage from my diode case all the way to 0, depending on the value of alpha. This is only the resistive load case. We did not do the inductive load case because it would be it's too complicated to draw it. And they just what they do in the textbook is they tell you, okay, we can simulate it if you want, but we will not do the RL load case yet for this circuit. How about if the load is delta connected? Sometimes you have motors that are connected in delta or loads that are connected in delta that you would like to also do the same thing. You would like to control the voltage, the 3-phase voltage applied to these loads. How would you do that? This is a certain configuration. In this case, if they were all diodes, what is the voltage across phase A. This is this resistor. I don't want to call it phase A because this is a it's a phase AB, I would say, of the slope. What would be the voltage across this resistor if all of the devices were diodes? Huh? VAB, exactly. It would be the line voltage VAB. And same thing on this, and same thing on this, right? So I will be applying the line voltages on the devices, on the loads, correct? So, which means I cannot use this voltage waveform plot, because here I was drawing my phase. These were my phase voltages, and here was my phase voltage, and then my line voltage is divided by 2. So it's not this one. It's the one we used before for that had my phase and line voltages. My phase voltages here will not be relevant. I don't care about them because what will be relevant is really my line voltages. So here I have this will be, you'll find this a lot easier because we said that anytime, let's go back to the circuit here. Anytime now devices thyristor 1 or thyristor 4 are on, right, then I'm applying line voltage VAB across this resistor, correct? And anytime thyristor 5 and 2 are on, I'm applying line voltage VAC across this resistor, right? So now if I look at my line voltage plots, if I look at my line voltage plots, this is VAB, VBC, and this is VCA, right? And then this is again VAB, VBC, right? So we said that anytime I turn on a thyristor in the phase where connected between phase lines A and B, this is, let's say, phase A, and this is phase B, and this is the resistor I have in here, and these are my 2 thyristors in here, right? And these are my 2 thyristors in here, and 2 thyristors in here, right? If I turn on any of these thyristors, then this resistor here will have phase AB voltage across it, right? Or line AB voltage across it. This is my line AB voltage. So if I provide a gate signal here, then this line voltage will be applied to my load. Do you agree? And then they call this, obviously, they will call this one. Okay, let me draw this A, B, C table again. And also 1 is this way, 2 is 1, 2. I'm looking at the ones in the same polarity. 1, 2, and 6 are in the same polarity. 1, 2, and 6 are in the same direction, and then 4, and then 5 and 3 are in the opposite direction. Regardless, this will not be important in this circuit, but let's look at it here. So if I turn on device 1 is looking this way. This is device 1. So if I turn on device 1 here, I will be applying phase A or line AB voltage across my load. So what is the corresponding current going to look like? Also the same, because I have a resistive load. So, and if I maintain the same sort of firing angle, then I will also fire the return. So this is 4. This is device 4. 4 is the return, the opposite polarity current. So 4, if I fire device 4 here, I get this voltage across my load. This is 1 and this is 4, right? And I do the same. I can draw it here, and then this will be. Did I shift it? So I shifted it. I don't want to shift it here. But this is what? The last portion, the last portion, the last portion, the last portion. Yeah, 0 here. This will be my voltage and my corresponding current. Right? For device, this is device 1 and this device 4 being turned on. This is device 1 again turning on and device 4 turning on. If I would like to do this, right? This is, again, the objective is to do what? If they were all diodes, what would the voltage across this resistor be? Line voltage VAB, right? If they were all diodes, I would get the full line voltage, right? If I would like to reduce the voltage, how do I do that? I can put thyristors like here for one of the phases. We did an example here. 1 and 4 are the thyristors you have on this across in series with this resistor. So if you turn on thyristor 1 here, thyristor 4 here, you got a much less voltage than what you originally had, the red. Of course, you can bring alpha. So alpha is measured from where? Alpha is measured from the zero crossing of my line voltage. Right? This is where I'm measuring alpha from. The zero crossing of my line voltage, because the diodes would have conducted in that case, right? So this is one condition. How about phase? How about the current in phase in this resistor between phases A and C? Okay. What if I sort of have the same firing angle? What sort of current will I get? Towards the end, I would get this pulse, right? And this is towards the end of the first half cycle. I would get this pulse, and then towards the end of the positive half cycle, I put a pulse here. Negative half cycle, I put a pulse here. Right? Positive half cycle. This would be the voltage across this resistor. If I fired what? 6 and 3. 6 is the same polarity as 1. 6 is fired here, right? 3 is fired here, right? If I fire 3 here and 6 here, assuming that 6 is the same polarity as 1, then this would be the positive current. Okay. How about the current here? Because this is important. Why is this important? Because this is now my source can be here, right? My three-phase source is here. And typically I'm worried about the current that's being supplied by my utility, right? I have my three-phase source here. This is my utility. This is coming from my utility, my source. And this is my load. Typically my concern is what? The power factor that the utility is seeing. The total harmonic distortion that the utility is seeing. That's my concern. Inside your load, you do whatever you want. You're a factory. You do whatever you want inside your factory. Burn it down. They don't care. But they care at the connection. The place where you are getting power from them, they would like to know what is the current waveform. Right? And what are you doing to the voltage waveform? Are you polluting the voltage waveform? Are you polluting the current waveform? So what's happening inside my load here? This is happening inside your load, right? This is the current inside these phases, correct? This is your concern. You're the one that has a problem with starting your motor. You want to start your motor with a lower voltage so you can not have the high starting inrush current of an induction motor. That's your concern. Their concern is the current that is being drawn from the utility, right? So if the current that's being drawn from the utility is their concern, so you will label this. Let's say I label this IAB. And then I label this, so this is current flowing here, IAB. This is current flowing through here. I'll call this IBC. I'll call current flowing through here ICA. Right? So my concern is the utility current. So the utility current, I'll call that IA. IA is the difference between these two currents, right? This is coming into the node, this is coming out of the node, and this is coming into the node. So the sum of IA plus ICA is IAB, right? So IA is equal to IAB minus ICA, right? So IA is equal to IAB minus ICA. That is your concern. This is what the utility is concerned about, right? So how do I calculate this? This is what? This blue one is what? IAB, exactly. And this green is ICA. So how do you draw waveform IA? IA is this minus this, right? So this is a positive, so and there's no corresponding ICA, so it's 0. And then how about here? The blue waveform is 0 and the green waveform is negative, so it's 0 minus a negative number, so this will be flipped, right? So the waveform would look like, the waveform from IA would look like this, right? Like this, and then like this, right? And then it will look like this, and then it will look like this. Right, I'm missing one here. Then I will have a negative here. I missed, one is not appearing. One of the humps is not appearing here, but it will look something like this. Two humps negative, two humps positive, two humps negative, two humps positive. This is my utility current, IA. This is obviously not a sine wave, and obviously has quite a bit of harmonic content here, right? So the utility would not like that, for sure. So they will ask you to do analyze, do your Fourier series, figure out what harmonics you have here, and put appropriate filters in that case, right? So this is one kind of shape for this waveform. How about if I make this alpha a lot less? What's going to happen to my IA waveform? If I bring alpha to here, this is alpha prime. Where will the blue start? Here. The blue will start here. How about where will the green start? Somewhere here, maybe, right? So the green will start somewhere here. And there will be a place where they are overlapping, right? You will just draw them. You will not get these hump 0, right? Because of what's happening here, they are intersecting. You were getting a hump and a 0 because they were not intersecting. Here they are intersecting, so the waveform will look a bit different, and they showed you the textbook. Just draw it out of practice, right? So here, the case where the currents don't intersect, and we drew that. And then the case where you started the current, the alpha is smaller, so the current starts earlier for the IAB, and ICA start earlier. There will be an intersection, so it will just look, it will look more funky. I don't know. Whatever. I don't know. I'm not sure if this will have more harmonics or less harmonics. You would have to, do a Fourier series and analyze it. But it just looks different. Like, these are the two conditions. Remember, in the previous case, we had the condition where 3 devices on, 2 devices on, no devices on. And then we had the condition where 2 devices on and no devices on. Here we have also two conditions where the phase voltages and currents, in this case, are overlapping, or they're not overlapping. Right? And at the end of the day, you're just trying to control what? The value, the RMS value of voltage or current applied to your load. You're obviously doing that. You're obviously doing something. You're changing the shape from a sine to something. And you can make it very small, you can make it 0 if you want, or you can make it like the diode case, right? And in between, it will depend on the circuit topology and what you have here. So any questions here? Now we'll just wrap up this chapter. Why did we study this chapter? It's mainly because the workhorse, or the most common application of this, is induction motor, not speed control actually. It's induction motor starting. And remember we said that induction motor speed control is done, you can only control speed if you are changing V over F. If you maintain, because V over F is proportional to the flux in the air gap. If with flux is what produces torque in an induction motor, right? So V over F, the way to control it is by, flux, to control flux, you need to change V over F. If I'm only going to change V, I'm not controlling flux. So I'm just controlling the voltage. If I'm bringing down the voltage, what am I doing? At the end of the day, the induction motor is an electrical circuit. It's a box here. It's a two-port network with a circuit inside. Right? You bring down the voltage, you'll bring down the current. So it's a way to reduce starting current in an induction motor. So this is the torque speed curve of an induction motor if you applied full voltage to the induction motor. You have high starting torque, and you're operating where typically you're operating at the point where, close to the, zero slip condition, right? Slip is the difference between the synchronous speed and the rotor speed, right? So you're operating where the difference is small, right? This is an unstable region of operation, right? Do you agree? This is, induction motors don't operate in this region. This is unstable region of operation. This is maximum torque that the induction motor can provide, and typically you're operating around the point where you have zero slip. So if your load, again, depending now your load, if your load looks like something like this, and we discussed that a load like this is typically a fan type of load or centrifugal pump type of load, right? But if your load is an elevator, why is it different than a load like this? A load like this does not require torque at zero speed. But an elevator has people in it, even when it's at zero speed. When you're going to start from zero, you're starting with a load. So you're starting with a load here, right? In this case, if you have a load like this, you cannot not have starting torque. You require starting torque to be able to support this load. So if you are going to apply full voltage, this specific motor will have a starting torque higher than your load, and then it will intersect, with the induction motor's torque speed curves in the stable operating region, right? If I'm, right after, beyond the peak, after I go beyond the peak with it for a while, with a little bit, then it's my stable region. This is my stable operating region. All of this is my stable operating region. So fine, this torque curve will intersect with my motor's torque speed curve here. Then you're fine. But if, in this case, you turn on your supply to the motor and you have a huge starting current. Typically induction motors, when you're applying full voltage, they will have huge starting currents. So, and if your facility cannot, withstand that, why would your facility not withstand that? Because, for example, let's say you have other loads next to you. If you have other loads next to you and you're pulling a lot of current, let's say you have your this is your supply, and then there's from your supply to this bus bar, there's a equivalent resistance, for example, and then you are also you're this load here. Also, there's an equivalent resistance of the cable between you and the supply, and here's another load. Right? Here's some important person's house. Right? If you draw a lot of current in this branch, what will happen? If you not less current. If you draw a lot of current, then what you will have is there will be voltage drop across this resistor, a large voltage drop across this resistor. If there's a large voltage drop across this resistor, then okay, let's take the case where there's no voltage drop across, where there's very little current. If there's very little current, then basically my supply current is reaching my loads. You agree? If there's no voltage drops, then my supply current here is the same as almost as my current, my voltage at this node. My supply voltage is the same as the voltage at this node. But what if there's a big voltage drop, huge current? If there's a huge current, then there will be a voltage drop here, another voltage drop here. So the voltage at this node is equal to, the voltage at this node is equal to the voltage at this node plus this drop plus this drop, right? Which means that the voltage here, which this other person was taking from, right? This person is using the same voltage that you have. this voltage now changed. It is no longer close to your supply voltage anymore. It's lower because of what you did, right? So in some cases, induction motor starting because of the very high currents causes other devices to fail or not run properly because of the reduction in voltage, right? So you don't want to do that. So the alternative is to do what? This. Bring down the voltage. If you bring down the voltage of your induction motor, you have these other curves that the induction motor operates on. These are other curves that the induction motor can operate on if you only bring down the voltage, change the voltage, right? However, the problem is, what happens is your induction motor starting torque keeps reducing. If you have a load like this, and you're trying to run it with this induction motor at a reduced voltage, it will not start. This will not start either, the load, right? So it depends on your load. If your load allows, like this compressor or centrifugal pump or whatever, typically if there's no flow, there's no flow. Then you start running the pump to pump fluid, then torque increases gradually, right? And depending on how high you're pushing this fluid or what the density of the fluid, etc., right? So in this case, you can start it with a soft start. It's called a soft starter. In industry, this is called a soft starter because you don't require the huge inrush current. So in industry, this is called a soft starter. This is what we're doing here. So this is really the workhorse of this topology. So this topology, the workhorse is this soft starter industry. You find it everywhere. All factories, everything, everywhere you find this soft starter. So this is one application. The other application that is very common as well is static VAR control. We said, I think we also briefly talked about this earlier, but this is another main application. Power factor. VAR is what? Is volt amperes, right? Volt amperes is what or reactive power. Is reactive power, you can control it by, how do you control reactive power? If you have a source here and a load, the voltage, the voltage and current here, the voltage between these two nodes and the current through this line will have, will either be in phase or they will be out of phase to a certain extent, depending on the load, right? The reactance of the load. If you want to change this, and I would like to change it sometimes because I would like the utilities require you to operate with a certain power factor. So they require that your voltage and current have a certain maximum angle between them, right? If you exceed that, then you're operating with a poor power factors, and the utility does not like that because they do not charge you for the reactive power. They don't charge the home consumers for the reactive power, but they charge, of course, they enforce rules on industrial consumers so that they stay within a certain limit, so that, because what they charge for is the active power, right? If they allow you to draw as much reactive power as you want, and they don't charge for it, then they're losing money, right? And they are buying equipment that is rated to a very large rating, and this rating depends on active and reactive power going through it. So they're not charging you for the equipment, they're not charging you for the power, then there's disaster for them, right? So they force you to operate within a certain power factor. So how do you do that? The way you would do that is alter the impedance that the utility is seeing. How do you alter the impedance? Put a capacitor or put a inductor or whatever, depending on if you're leading or lagging power factor, right? So you put some impedance. Sometimes you can put a fixed impedance, and that will work. But sometimes you cannot live with a fixed impedance, right? So if you cannot live with a fixed impedance, and why can't you live with a fixed impedance? Because sometimes your loads are changing, right? Your motors are on, so you're a huge inductance now. How about if you turn off all the motors and you're just lighting loads? Then you don't have this huge inductance anymore. It's a very small inductance, right? So your power factor change considerably depending on the time of day, depending on the loads, right? So sometimes this change is slow. If this change is slow, then I can add fixed elements, but I can also add switched elements. I can switch capacitors in and out, or I can switch inductors in and out to control my power factor. And they will be mechanical switches, right? That's one option. The other option is cases where your loads are changing very fast. That you have like cutter steel load are changing very fast, or other loads that are changing fast. In this case, you would like to control this electronically. You cannot have these manual switches or circuit breakers or whatever. They're not manual. Somebody's sitting there and pushing them, but you have a push button or they're controlled remotely or whatever. But they're still mechanical switches. You don't change the value of when you connect them. You're connecting the voltage across the capacitor. But what if you want to connect half the voltage across the capacitor? You cannot do that with a mechanical switch. The way to do that is with power electronics. So with power electronics, I can put a thyristor looking down, and I can put a thyristor looking up. This way I can control current through this inductor in both directions, right? And I can control it to whatever I want it to be, right? If I apply small alpha, then I'm putting a big voltage across this inductance. Large alpha, large delay angle, then I'm putting only a small voltage across this inductance. So the current here is going to be different, which means that the utility will see an inductance as if it's a smaller inductance, or as if it's a larger inductance. It's like you can play with the value of inductance, and you can do the same thing with the capacitor as well, right? So static VAR compensation is the other workhorse of this circuit that we're studying in Chapter 5. These AC voltage controllers. These are the two main applications of these AC voltage controllers. The other main application is dimming, but now with lighting becoming LEDs and fluorescence and stuff like that, that's not really the case anymore, because with LEDs you need to change the voltage, yes, to control the current, but it's a DC to DC converter. It's not an AC to AC converter anymore. With incandescent bulbs, it was like that. With these incandescent bulbs, you had these. You go buy these devices that just a rotary switch that you turn around, and basically it has a thyristor inside, and you're changing the firing angle. Now with LEDs, it's very different, or fluorescence is very different. Yeah. Okay, so that's the end of Chapter 5. We can start Chapter 6, or we can just leave 5 minutes early today. We can leave 5 minutes early today. So next time we'll start Chapter 6, which is the DC to DC converters. Okay.